Okay, number 6. A town's population B can be modelled by the equation B equals AB to the power T, where A and B are constants and T is the number of years since the population was first recorded. The line L illustrates the linear relationship between T and log 10 of B for a period of 100 years. The line meets the vertical axis at 0, 5 and has gradient 1 200. Part A, write down an equation for L. Okay, so it's a straight line. We need to be thinking of y equals mx add c, except y is log 10 b and x is t. So it's going to be then log 10b is equal to 1/200 times t, so t over 200, plus 5. Okay then, part B wants us to find the values of A and B. So to do that, we need to transform the exponential model into logarithmic form so that it works with the straight line. So we know that P equals AB to the power T. Now if we take logs of both sides, we know log 10p is equal to log 10 of AB to the T Now we need to split the log on the right, so we can say that that is log 10a add log 10b to the power t. Now with that second log, we can use the power rule and write it as t log b. So to make it more relatable to the equation of the straight line from part A, I'm going to write this as log 10b is equal to t log b add log 10 of a. Okay, so log 10a is the constant at the end, so log 10a is equal to 5. Now that's saying 10 to the power of 5 is equal to a. So a is 10 to the 5, which is 100,000. Okay, and now then log 10b is the gradient because it's multiplying t. So that means log 10b is equal to 1/200. So that tells us b is 10 to the 1/200th, which to 3 sig figs gives us 1.01. So what we can now do is write the exponential model with these values in. So we can now say P is 100,000 times 1.01 to the power t. And part C, with reference to the model, interpret the values of A and B. Okay. So, when t is equal to 0, P is equal to 100,000. So, 100,000 is the initial population. Okay, and then the 1.01 well, this is now like compound interest from back in the old GCSE days. So this tells us the rate of growth per year. So how that works is it's like compound interest from GCSE. If you multiply something by 1, you're just finding 100%. 0.01 increases it by 1%. So the growth rate by the model is 1% per year. Okay, then the part 1 wants us to find the population predicted by the model when t is 100, giving our answer to the nearest 100,000. So, all that we're doing for that is putting in t equals 100. So for that I get P is 270,481. So to the nearest 100,000, that's 300,000. Okay, then for the part 2, we want to find the number of years it takes for the population to reach 200,000 according to the model. Okay, so this time we set 200,000 is equal to 100,000 times 1.01 to the power t. Now we can make that a lot nicer by dividing through by 100,000 and we get 2 is 1.01 to the power t. now we need to get the t down, so let's take the logs of both sides. So I'm going to use natural log, so log 2 is equal to, now when we do this, we're going to get a log 1.01 to the power t. Using the power rule, that's t log 1.01. Now divide both sides by log 1.01. And that is going to give us t is 69.7 years. Okay then, for part E, we want to state 2 reasons why this model may not be appropriate. Okay, so first up, we have the classic problem that there's no cap or limit to the model, so it predicts infinite growth, which can't happen, so that's one problem. Okay, now the other thing I would say is that the model is being used to predict growth over a period of 100 years. 100 years is quite a long time, so it's very unlikely the population will continue to grow in the same way over a long period. Another thing we could say is the population may be affected by influences such as disease or people moving away for whatever reason. Okay guys, that's number 6 done. One more to do, and let's go on to number 7.